Okay, now we are live on YouTube. And where's the slides for the day? Okay, so today, most of the today is on math. So it's a little bit dense, but this is sort of some of the concepts you might have already seen in various other classes, especially things like graph theory. But most of the content here today is coming from two subjects. One is point set topology. Topology, I should be able to spell today. And then one is algebraic topology. Okay. Before I do that, I actually want to also go over verbally some of the specific items I added to the syllabus to support student well-being during COVID. As you see that, most likely the whole spring semester is going to be completely online, and hopefully everybody will get vaccinated in the summer. But at the same time, I understand that it's very stressful to try to go through Zoom meetings and so on. So this is some sort of specific COVID-19 accommodations. So the first thing is that for assignments, of course, not including the last final project presentation report, is that you can get a one-time 2-day extension without any penalty. So you should email the TA and CC me, the instructor, to request the extension before the deadline. The second thing is that, to be clear, this class do not have a credit/no credit option. Feel free to email me if you have questions. So again, another thing is that since our things is live stream on YouTube, so you can contact me if you do not want to be recorded at all. And then we have a few suggestions to work around. One is to turn off your video. One is to use a pseudonym for your Zoom name display. And if you don't feel like asking questions directly through the audio or the video, you can use the Zoom chat, and then the TA will read your question to the class. Okay. The next thing is that this is probably the most impactful, is that there would not be, I would try not to have any assigned work in the week that is traditionally spring break, even though we don't really have a spring break, but we want to reduce the cost load during that week anyway. So it's March 7 to 14. And then March 9 is something I call Student Wellbeing Day for this particular class, where there's not going to be a lecture. So that is a day where you can take a break, go hiking, relax, or binge watching on Netflix, whichever you want to do, have a middle of the week break. The next thing is that we'll also try to have a 5 minutes biological break during regular lecture time. And of course, the TA have to remind me, because once I start teaching, I'll just like go full force. So interrupt me if you want to. The break is going to be around 9:40, between 9:40 and 9:45. So we'll take a break at 9:40 and then come back at 9:45.
Yeah, I have an alarm set up.
Okay, great. But interrupt me once I finish my sentence. So then the next thing is the student. Oh, I mean, like when I'm actually in the middle of the instruction, like maybe wait until I finish that particular slice or whatever, and you can interrupt me. Of course, during my lecture, feel free to interrupt me with any questions. I'm meant for this lecture to be pretty casual, and I would like people to, learn if there's something confusing. So ask me a question anytime. The last one is that every student can take additional mental health days, 3 mental health days, which means that you can take the day off from the lecture, from this class, any day you want. And it's similar to some sort of excuse absence, right? So if you just say, okay, somewhere in April, I'm just too overloaded, burned out, I'm just going to take today's off. That's fine, because everything is recorded on YouTube and you can always come back and watch it at your spare time. So the hope is that those implementation can help you to try to kind of balance work and relaxation under stressful situations, and go out and enjoy the nature a bit. Okay. if there's no questions, let's dive into all the math we have to talk about today. So today is mostly focusing on theoretical foundations, a lot of definitions, some topological concepts you may or may not be familiar with, but that's okay. Interrupt me anytime. I mean, I would say that the subject of point state topology and algebraic topology are both very, very fun subjects. There's a lot of interesting scenarios you can kind of dig into, but the starting point is to read the relevant chapters in the textbook. Okay. So another thing we have left from the last lecture is what is the homology of a torus. Remember when I say homology, zero-dimensional homology is connected components. One-dimensional homology is loops or tunnels, and two-dimensional homology corresponding to voids. Right, and then of course, high-dimensional topology homology corresponding to sort of voids of higher dimensions. Okay, so another way you can think about this is, in specifically for manifolds, that there's specific way to compute the number of tunnels, which has to do with the concept of genus. But before we go into the detail, do we have a volunteer? Right here is my double torus. So think about it's a surface of a donut that has two holes in it. Okay, you can actually get it in our downtown a donut shop, and hopefully in traditional classes this is the time where I actually bring 2 dozens of donuts to the class. Unfortunately, everything's online, so hopefully next time you go through a donut shop you will be thinking about homology. Okay, so here is thinking about how many. So first question, Betty 0 corresponding to number of connected components. So how many connected components do we have? Go ahead, Jordan.
Just one.
Yep. Right. So when I say connected component, that means if I start with a point, any point on the surface of this double torus, there is a path I can reach. Okay, so path connected, and we'll define what's path connected mean. I'm going to leave the second question last, but how many voids do we have?
Also one.
Also one, right? So remember, the voids are sort of the separation between inside and outside, right? If I somehow pinched my double torus, or I just get a pinched torus. What is a pinched torus? So this is a torus, and this is a double pinched torus. Okay, so I kind of take the boundary and then can snap it into a point. Then this one has two void because the two sort of empty inside the pocket of air, they don't connect into one another. In this particular case, the pocket of air inside of this double torus is actually all connected. So it's actually one empty space. So it's sort of one void. All right, the last bit is what is the dimension 1? So how many tunnels do I have for this? Remember, this is hollow in the middle, right? It is not a solid thing. It's the surface of a double donut. So what is Betty 1? Do people have a guess?
I have a guess.
What's that?
I have a guess.
Yeah, go ahead.
Is it 5?
Okay, number 1 guess is 5. Okay, who else has a guess?
4.
Okay, the answer is actually 4. All right, so, but you're close. Okay, so what's happening? Maybe first erase the surface. There's 2 obvious tunnels, and they're in some sense independent from each other. So there's a tunnel right here. There's a tunnel right here, right? And then other 2, essentially think about it as sort of the circles surrounding the band. So okay. So it turns out, so the answer is 4. So it turns out that for this specific type of manifold, which we call the surface of a double, the double torus is a specific type of manifold. and specifically it's connected and it's oriented. It's actually a surface. And then there's a concept of what's called a genus. A genus is of a connected orientable surface. Of course, we'll define what is connectiveness mean, and later on we'll define what is orientable mean. Orientable on the high level is that if I triangulate the surface, I can assign an orientation over each of the triangle on the surface, and I can do this assignment in a consistent way. That is what the orientable mean, but we'll define it more mathematically later. But in this case, think about the double torus is actually a surface, and then the genus of the surface is an integer representing the maximum number of cutting along the non-intersecting closed simple curves without rendering the result manifold disconnected. So that is the definition of a genus. So what is how many genus do you have for this double torus? If I take a pair of scissors and start cutting, right? Like, remember the cutting surface cannot intersect. So how many cuts can I make to disconnect it?
I think it's 5 again.
Okay, it's actually, let's see. Interesting. I think this is actually non-intersecting closed simple curve. Yeah, it's actually 2. Okay. So first of all, and then this 2 has to be a little bit careful how you cut. For example, I can cut here and I can cut here, right? The remaining things are connected. But if I do one more cut, let's say this is my first cut, this is my second cut. If I do the third cut, all of a sudden I disconnect my surface. Right? So the number of genus for this is actually 2, which is I'm using G as a representation. And there is actually a formula that for closed oriented surface, its first Betti number, which is number of tunnels, and its genus is related by the formula that the first Betti number is 2 times the genus. So because the genus is 2, so the first Betti number is 4. Okay. And an intuitive way of thinking about this is that if you think about a single torus, or which is a classic torus, okay, it always have two loops. It has a loop goes around. It has another loop that goes around the surface. So what's happening is that when I am creating this double torus, what I do is I take 2 of those single torus and I kind of glue them together. So what I do is I kind of do a small cut right here. I do a small cut right here and I glue them together. Okay. And in this particular case, of course, this is not a proof of this general theorem, but this is just a validation of this, is that, you know, in the torus itself, it has already 2 loops, and when I glue them together, and then the gluing process does not destroy those loops, so I have twice the number of genus that's there, right? Because if you think about what is a genus for a single torus, a torus has a genus of 1. Because if I cut it once, it still remain connected, but if I cut it twice, it disconnected, right? I can do once, and the second cut is going to disconnect it. So the genus is 1, okay? All right, this is just a small taste of, actually there's a formula for orientable 2 manifolds through this kind of gluing operation. If we have time, we can go over that, but otherwise this is a subject under algebraic topology.
Are you allowed to cut it along the other axis, like you're slicing a bagel?
Oh, yes. But remember, you have to count along a non-intersecting closed simple curve. But remember, it's a maximum number, right? if I cut along as a bagel, I see what you mean. Let's do this, right? You can argue that even for a single torus, if I cut along exactly the first generator, like this, right? This is how you cut a bagel. The surface get disconnected. But remember, it's asking for the maximum number. This is not the maximum number. The maximum number is 2.
Okay.
I think this kind of confused me also. And
Yeah. So think about this, right? I want to cut my surface, but such that I do not disconnect it. So you have multiple ways to cut it, but I'm saying no matter how you cut it, the maximum number of cutting you can do without disconnecting it is 2.
So for the double torus, if you make the cuts 1 and 2,
yep,
and then sort of deform it, it can expand it so it looks like a basketball with 4 holes in it.
Oh, no. You have to be a little bit careful. The moment I cut 1 and 2, it's no longer have a void. There's no basketball left.
Well, a basketball with like 4 punctures in it. So a sphere with 4 sort of holes in it.
Well, yes, okay. But then you need to do one more. And now my argument is if you do one more cut, right? Remember, is a non-intersecting closed self-loop, simple loop. So you have to cut along a loop, right? So no matter how you cut now, once you have flattened it, well, actually, you cannot completely flatten it after 1, 2, still kind of a tube left. So no matter how you cut, you're going to disconnect the surface.
So I think what I'm missing is a closed simple curve.
Closed non-intersecting closed simple curve. So if I have the surface, let's start with a simple example. Okay, let's start with a simple example of a basketball. Okay, what I drew here is a simple, not self-intersecting loop, but this is it's a closed loop, but it's not simple. Okay, so simple, and there's definitions, is non-intersecting, so you don't intersect itself. So think about, so that those are the definition of it. So in your case, when you have the double torus and you already cut it in twice, let's say I cut it right here and I cut it right here, right? What's remaining, the argument is that if I cut one more time with this kind of simple closed loop, let's say if I just cut it, see the pink cut, right? I kind of cut just a surface, a little loop. This flap of it is going to be disconnected from the rest of it, okay? If I cut along here, of course, you are going to disconnect left from right. Same thing if I cut here, because I already have the first and second cut, this entire piece is going to be disconnected. So by however you do, you cannot make 3 cut along self-intersect simple loops such that the surface remain connected. All right. Okay, so that's sort of like a small taste of the space of 2 manifold. It turns out the space of 2 manifold can be completely classified, and then that's again, a very fascinating subject in topology. But today, let me start with the foundations. Let's start talking about graph and connectedness. So a lot of those concepts you might have seen before, but if you haven't, this is a quick review. And this is corresponding to the book chapter 8.1. So graph in data science shows up a lot. One of the most common known ones are things like social network. For example, I can construct a social network where each node of the graph is a user and each connection is, whether something is liked over Facebook. That's one type of connection. The other type of connection you can have is if for one node and another node, it changed some number of emails over the spans of a week. So in terms of communications and so on. And the other sort of connections can be, not only I require A has to like B's post and B has to like back, or A have to follow B and B have to follow A at the same time. So a lot of analysis and study of social network, the first step is boiled down is how you model your data. And depending on how you model your data, you are going to get sort of the next, you're going to get a very different graph representations, okay? There's other type of analysis where the node is in the social network is no longer a person, but maybe an entity, right? So I could add other entities. For example, if all of those people belongs to a particular university, then the university can be a node where everyone has a connection to this university as an entity. So essentially that the node in a social network does not have to be an individual, but it can be an organization, and so on and so forth. So you can, if I go beyond it, graph is of course the most natural and widely used modeling of social network. The next thing is hypergraph, where is that not only I have a node, let's say each of the node is again a person, but I have, instead of edge that connect a pair of entities, I'm going to have edges that connect, say, pairwise or every 3 entities. For example, in this case, my red edge is what's called a hyper edge that connect all 3 entities. And there is actually an active research area I myself involved is using topological data analysis to study hypergraphs, right? So one of the classic hypergraph of how people study is called authorship hypergraph. So authorship hypergraph is in the situation where each node is an author, and then there is a hyperedge, which you can think about it as a set or a collection of authors who wrote a paper together. For example, in this case, I have 4 authors, and then one of the hyperedge, the first red hyperedge corresponding to 3 of the authors writing a paper together. The second hyperedge, which is also an edge by itself, is including, the authors C and D that wrote a paper together. And you can, of course, go higher. And in this case, we can say that this hyperedge is a edge that represents a paper that is written by 4 authors, A, B, C, D, E, F, G. Okay. So yeah, so there is some existing both on the theoretical side and the algorithm side and implementation side to use TDA to study hypergraphs. All right, coming back to graph, is that we need to start some fundamental notions of graphs. So the first thing is abstract graph. An abstract graph is a pair of a set of vertices and a set of edges for each pair of vertices. So another way people sometimes write is V is a collection of vertices and E is a collection of edges, and E sometimes you can written it as a subset of V cross V, right? So this cross product just means that the edge is represented by 2 of its end node, where each node or vertices is it's part of the vertex set. Okay, and of course in here I already give example on the lower right corner is an example of a graph. So one thing you have to be careful, if I say your data is a graph, it does not mean the graph is connected. Okay, so for example, in this case, this is an entire graph, but this graph has 2 connected components. The node 0 forms its own connected component, and the rest is another connected component. All right, so of course, there is definition of what's called a simple graph. A simple graph is that if no 2 edges connect the same 2 vertices and there's no self loop. So for example, this example on the right-hand side, this is not a simple graph because it has self loop, which is right here. And it also has multiple edges connecting pair of nodes, okay? So because this is not a simple graph, I can make it simple by maybe removing some edges. For example, I can remove a duplicated edge between node 1 and 3, and I can remove the self loop. And now I just made it into a simple graph. Okay, so in data analysis, sometimes when your data comes in this form, depends on your analysis tool and depend on your end goal, you might have to do some pre-processing to kind of model your data. Of course, when you model your data, you may lose some information that may or may not be important for your analysis task. Okay, but it's very important, especially for sort of social network analysis. A lot of energy is actually on what we call data wrangling, which is the first step of how do you take the raw data and model it as either a graph or a hypergraph, either as a weighted graph or unweighted graph, as a directed graph or undirected graph. Okay, so all those are relevant concepts for graphs. Okay, so the ones that is relevant to today's topic, another concept called complete graph, right? Complete graph is basically there's an edge for every pair of vertices. So both the first picture and the second picture I show here is a complete graph. For example, the first picture I show at the bottom right here, it has 5 vertices, and then there's pairwise edges between them. And this one has, of course, a larger number of vertices, including the one in the middle, and we kind of drew all pairwise edges, okay? And a regular graph contains vertices with the same degree. So actually, both this example on the left is also a regular graph because every single node has degree 4. Okay, so degree is equal to 4. So what is a degree? Of course, the degree is basically number of neighbors for a given vertex. Okay, so now, or another way to describe it is number of edges that is adjacent to this vertex. Okay, so those are fundamental concepts from graph theory. So hopefully this is a quick review. Of course, stop me anytime because I know that not everybody have seen those concepts before.
Hey, Bei, shall we take a break?
Yes, good, thank you. So 5 minutes break, stretch your leg, do some yoga moves, and we'll be back in 5 minutes, 9:48. All right, let's resume the lecture. And Faye, thank you for reminding me, because as you can notice, once I start teaching, I just completely forget about the time. So okay, so once we have understand what is a complete graph is, the K of n is sometimes used to represent a complete graph with n vertices. So for example, K of 3 is basically a triangle, right? And K of 4 is, you have those 4 nodes, and every pair you have a connection between them. Okay, so it turns out the complete graph of n vertices also represent the edges of n-1 simplex. And we're going to see a mathematical definition what a simplex is. But on the high level, a zero-dimensional simplex, so this is a zero simplex, is a vertex, okay? So a zero-dimensional simplex has one vertex. A one-dimensional simplex is an edge. A one-dimensional simplex has 2 vertices, and a 2-dimensional simplex is a triangle. When I say triangle, it includes its interior, and a 3-dimensional simplex is a tetrahedra. All right. So essentially, a k-dimensional simplex has k plus 1 vertices. Okay. And on the right-hand side, I'm showing you a triangulation of a torus. And again, in here, the zero-dimensional simplex is the vertices, the one-dimensional simplex are those edges, and a 2-dimensional simplex are those triangles, okay? The reason I'm giving this particular example is this is actually how you want to represent a surface in the computer, right? Instead of the most likely representation is going to be represented as a collection of vertices, edges, and triangles. And together it described a computorial representation of the surface, and you can operate over those vertices, edges, and triangles for your computation. Okay, so in some sense, in sort of geometric processing and computer graphics, those simplices already showed up. And of course, the collection of all those vertices, edges, and triangles, if they satisfy a certain condition, is called a simplicial complex. And we're going to see a definition very soon. Okay, so again, going back to graphs, the last bit I want to mention is that the complete graph with n vertices will represent the edges of n-1 simplex. So K of 4, which is a complete graph of 4 vertices, it's also corresponding to the boundary of the 3 simplex. When I say it's a boundary or edges of, actually in this case, it's the edges of it, is because the 3 simplex is this piece of solid thing, includes its interior, while the complete graph is only the edges of the simplex, okay? But that's a relation between the complete graph and a particular simplex, because essentially, for a simplex to be formed, there's an edge between every pair of vertices in the simplex. All right, so the next thing is the notion of connectivity of a graph, okay? A simple graph is connected if there is a path between every pair of vertices, okay? So again, this is a connected graph because for any node, let's say A to any node B, there is an edge between them, which is this yellow path, okay? But of course, if I add another node C and maybe D in this is a whole graph, this is no longer a connected graph because I cannot reach from A to C, okay? So a connectivity essentially has to do with, is all pair of nodes reachable from one another, okay? And then the connected component of the graph is a maximal subgraph that is connected. For example, in this example, what I circled here, this is one connected component, and the node CD form another connected components. Of course, I need to, in this definition, there's a definition of a path. So what is a path? A path between two vertices is a sequence of vertices with an edge between adjacent vertices. So for example, in the picture I just drew, let's say, well, actually let me draw a new graph. Okay, then a path between node 1, let's call it V1, or since we're doing U and V, let's use the same symbol. I have U and V. The path between them is U goes into, this is U is equal to U0, and then this is U1, this is U2, this is U3, and V is the last one, is U4. So the path is basically all the nodes that lead from one node to another, okay? And the simple graph, the definition of a simple graph is all the vertices that you visit are distinct. And if it's not simple, that means they are not distinct. If they're not distinct, that means you visit one node and come back to it. That means there's a loop in your path. All right. A path length is number of edges that is traversed. In this case, the example I gave, this is a path length of 1, 2, 3, 4. This is a path of length 4. That's you traverse four edges. Okay. Interrupt me if you have questions. All right, so the next thing is the definition of a tree. A tree is actually a special type of graph, right? A tree is an undirected graph. Okay, so of course I haven't defined what is a directed or undirected. Edge with direction. If I have a graph whose edges has direction assigned to it, those are directed graph, otherwise it's undirected. So a tree is an undirected graph in which any two vertices are connected by exactly one path. So for example, the classic way to draw a tree, this is a tree. And for any two nodes, let's say A and B, there is a single path between them. Of course, if I go to the previous example between node U and V, there is actually multiple paths, right? The yellow is one path, the orange is another path. But the definition of a tree is interesting, is that there's only a unique path between any two nodes. For example, if I actually add one edge, let's say right here, all of a sudden it broke this uniqueness condition. And also it means that, for example, in this case, because I added this extra dotted edge, this is no longer a tree. And going from A to B, I have alternative path, okay? So essentially the moment I introduce a loop in my underlying structure is no longer a tree. And that loop also broke the condition of unique path. The smallest connected graph is a tree. So what do I mean by that? If I have n vertices and I want those n vertices to be connected, the smallest one is a tree, which has n-1 edge, okay? Of course, you can validate it, and then of course there's a proof. I'm not going over the proof, but let's say I have 3 nodes, so n is equal to 3. In order for them to be connected, I need at least 2 edges to connect them, okay? And now this is a connected graph, but it's also a tree. And another interesting component is that if I have a tree, if I deleting any edge, for example, this edge, it's going to disconnect the tree, right? This is sort of goes hand in hand to the previous statement, is that the smallest connected graph is a tree. That means I'm going to connect all the vertices with the smallest number of edges. And if I can actually delete one more edge and still remain connected, then it's not the smallest number of edges and connect them. So you can actually prove by contradiction. But in this particular case, the property of a tree is that if you connect any edge, it's going to disconnect the tree. And then lastly, it's called the spanning tree. If I have a graph, a spanning tree is a tree who share the same vertex set. So it's the same vertex set of the graph. And the edges is a subset of the graph edge, and such that it's a tree, okay? So what I drew here is a tree from the underlying graph, And you can see that there is a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 vertices from this graph. So my tree has to go over all those 10 vertices. But then I'm going to, it's a subgraph in a sense that it's going to choose a subset of the edges to connect them. But also the one very important concept is called minimum spanning tree, is in the case where in case I have weights over my edges. So for example, in here, all my edges in my graph has an integer weight. Then the minimum spanning tree is a tree whose sum of the weights along the edges in the tree is minimal. Okay, so minimum spanning tree shows up in data analysis when you're thinking about route planning, when you think about how you put like, and also shows up when we actually later on talking about how to compute persistent homology. And the minimum spanning tree is going to show up there as well. Okay, but of course, remember, not all spanning tree is minimum spanning tree, right? So, the spanning tree is any tree which is a subgraph of the graph such that, it spans all the vertices. And that's a spanning tree. A minimum spanning tree is the one with the smallest total weights, okay? And also another condition you want to remember is minimum spanning tree may not be unique. That's another condition. Okay, so the reason we're going through all those concepts is a graph is essentially a special type of simplicial complex, but it's also a simple type of data that arise in practice all the time. But we want to introduce some concept that is inherently topological. For example, the definition of connectiveness and the definition of separation goes hand in hand, okay? So now the definition of the separation of a graph is that a separation of a non-trivial partition of the vertices, a separation is a non-trivial partition of the vertices. That is, I'm going to separate the vertices in two sets such that their union is a whole vertex set, but then there's no edge connecting from vertex in the first set to vertex in the second set, okay? So obviously, the concept of separation is connected to the notion of connectiveness. So a simple graph is connected if and only if it has no separation, right? So what does this mean? If I have this graph, remember this is an entire graph, and this is not a connected graph, because I can build a separation between them. So this is U set. This is W set of its vertices, and there's no edge between them, okay? So because this has a separation, therefore this graph is not connected, okay? And similarly, there's another related thing is that a simple graph is connected if it has a spanning tree. So for example, the picture on the left, this graph is connected is because I can find a spanning tree. This is not surprising because of the definition of a spanning tree. Remember, a spanning tree is a tree that connects all of its vertices. Once you can connect all of its vertices in a tree, there's a unique path for any two pair of vertices, which means that the graph is connected. Okay, I just went through a proof. It's very fast. So yes, what's the question?
I want to ask if the simple graph actually make difference, like if it's not a simple graph, are those two statements also correct?
Ah, very good question. Let's see, if a graph has self loop, what's going to happen, right? Let's say I have okay, and I add a self loop. Yeah, actually, I believe my conjecture is that this statement still holds if you replace it by not simple graph. For example, this graph has a self loop, and this graph has maybe a double edge. But I think most likely those two statements will hold, even if I get rid of the condition of the graph being simple. But to make sure, I would suggest you go through a proof. Okay, I think it's most likely true, but I couldn't find a counterexample at this moment. But oh, no, hold on. There's very important spanning tree. You have to be careful what you define as a spanning tree here. So actually, in fact, spanning tree is going to, by definition, not including the self loop and not including the double edge. Because you just not, so for example, in this case, 1, 2, right? The spanning tree is only going to choose one of those edges, not both. Otherwise, it's no longer a tree. Okay, but I think my conjecture is that if I replace the word simple from the statement, it's going to be true, but it would demand a proof. Okay, and it would be good to think about if you can come up with a proof. What the conjecture is if I remove the simple from my description. Of course, you still want to assume the graph is, say, undirected in this case. Okay, so one of the classic algorithms to test the connectivity of a graph is perhaps through search. And then there's two types of search. One is depth first search and one is breadth first search. And both of those are sort of a classic techniques from, if you're taking algorithm class. And then the underlying structure to store a graph is coming through union find. And we'll spend some time next lecture to talk through, well, actually there's a little bit context towards the end of the lecture about union find, but let's first look at what does depth first search mean. So if I have a tree, the ordering on the left-hand side is the ordering of how you visited the node. The depth first search is I'm going to go deep first until I reach to the root, the leaves of the tree, and then I kind of trace back. For example, that's why I start with node 1, and I go deeper, 2, and go further, deeper. When I say deeper, I'm going to say, I'm going towards my leaf. So 1, 2, 3, 4, that's sort of my first search. I'm visited all those 4 nodes in my tree, and then kind of trace back on my path. So I'm going to trace back 5, 6, and 7, and then go to the other side of the branch, 8, 9, 10, and then 11, 12, right? So in some sense, it's greedy that I'm going to go deep before I go to the rest of the branch. Breadth first search is, on the other hand, is that I want to kind of look at all my neighbors in the next step, and in the next step, and in the next step. So in this case, I start with node 1. I'm going to look at my first step neighbors all together. So 2, 3, and 4 are all my immediate neighbor. And I'm going to look at their neighbors, which is 5, 6, 7, 8, and then of course 9, and their neighbors as well. So, it's actually very much just looking at the notion of this gives you an idea how you traverse a tree. Okay. Now, for the remainder of class, I think we'll have time to go over some definition of topological spaces. Everything here now coming from point set topology. And some of them is quite interesting, just by definition itself, okay? So you're going to see this concept shows up of a topological space, okay? A topological space is a pair, where the first element of pair is a set, and then the second element of the pair is a collection of subsets of the first one, okay? So the condition of this forming a topological space has to be the empty set and the set itself is part of the subset, okay? Everything right now is very abstract and we're going to go over examples, okay? So the first condition is empty set and the set X itself has to be part of the collection of subsets. And arbitrary, meaning that finite or infinite, union of member of this collection of subsets has to be part of the subset, okay? So union of the element has to be in there, and intersection of finite number has to be in there. Of course, those are for technical reasons why we need finite versus infinite. But on the high level is the empty set and the set itself has to be in U. And then union of the elements has to be in U. And intersection of a finite number of members has to be U, okay? So now the elements of this set is called open sets, and the collection is called the topology, okay? So this is extremely abstract if you have not seen it before. But let's figure out the definitions and we'll see the examples. For example, now this pair is called a topological space. And sometimes when we talk about topological space, we assume that this collection of subsets is well understood. So we just call X to be a topological space. Okay. So what is example? All right. So here is a bunch of examples where I am using I'm using this symbol to be represent the empty sets. Okay. And what we're looking at is you have a 3-point set. So your 3-point set X is 0.1, 0.2, 0.3. And for example, the first picture here is saying that the U contains empty set, the set X, and that's it. Okay. And then the picture on the right-hand side, or maybe this one, is again, my X is 1, 2, and 3. And my U is empty set, the set itself. The set contains 1, 2, and then the set contains 2, 3. All right. Okay, so what are we doing here? We're going to say that for all those pairs we have, remember it's a set itself and a collection of subset of the set, which ones form a topological space. Okay, so let's start with maybe I'll choose this one. Okay, this forms a topological space. What is this? This is X is equal to, again, 1, 2, and 3 for this example. And then the U is empty set, the set itself. The set itself is, this whole circle. And it has a set 1, 2, subset 1, 2, subset 2, 3, and subset 2. Okay. So what you want to check is the 3 conditions. The first condition is the empty set, and the set itself has to be in the collection U, which is true. The empty set and the collection itself, which is 1, 2, 3, is in the collection. And now the second condition, remember, is to say the arbitrary union. So if I take union of 2 sets, if I take union of any sets, finite or infinite, they are together. So for example, if I take 1, 2 and 2, 3, I take the union, that's 1, 2, 3. And 1, 2, 3 is X itself. So that is in the that is there. If I take union of 2, union 2, 3, it's also the result is 2 and 3, it's there. So you check for all pairwise unions, and the end result is always there. And now you want to take pairwise intersections. So the third condition is if you take pairwise intersections, the intersection of finite number has to be inside. So specifically, if I take the intersection between the set 1, 2 and 2, 3, what is in the intersection? Anyone?
2.
2. Yeah. So 2 is also in the set. Okay. So that's precisely how I check for this form a topological space. But now let's look at this example in my yellow box. Okay. This is an example where it's not a topological space. Can someone tell me which part of the condition is violated, giving the space X as a collection, as a set X, and then the set of subsets U? Which condition is violated?
The intersection.
Exactly. Because if I take the intersection of 1, 2, and 2, 3, by definition, their intersection has to be there, but it's not because the intersection is 2. So this is not a topological space. And I will encourage you to check the other example that is not a topological space as well. Okay. So this is a situation of a topological space. So what is a classic topological space that you have been working with? It just you are not aware it's a topological space. A real line is a topological space. Our two-dimensional Euclidean space, a plane that goes to infinity, is a topological space. So let me try to visualize it, why this is the case. A real line is a line, okay? So what is my subsets in here? My open sets. My open sets are essentially open intervals on here, okay? So let me just use a different color to correspond to a different interval. All right. So if I take, for example, the red interval, again, I have talking about open interval. If I take the red interval and the green interval, if I take the union is again an open interval, which is also part of this topological space. So in a way that, think about the topological space R to be essentially actually it can represent it. What is my corresponding X? My corresponding X is a collection of all open intervals. And my U is a subset of X that is infinite. It has an infinite number of elements. So for any two open intervals, if I take their intersection, if there's zero intersection, it's empty set, it's in U. And if they're not, if they overlap, then the intersection of two open intervals is also open interval. Okay. So that's the first example of a topological space. The second example is imagining I have this R2, which is Euclidean space, and my set elements are those open disks. Okay, so again, it's the same thing. If I take two open disks, if I intersect them, that is still an open disk. If I take the union, that's also an open disk. Okay, so R2, or the plane Euclidean space, is a topological space. Right? There's many other examples of a topological space as well, but those are the ones that you work with. So of course, I need to define what is an open set. Okay, so yes.
So maybe in previous example, X is just R.
Yes, X is just R. Yeah, and then the U is a collection. Sorry, let me make clear. U is a collection of all open intervals. Yeah.
And their unions.
Any open interval can be described as intersection or union of other open intervals. All right, so this is
disjoint union of intervals.
The open sets. So let me put it this way: the open set for the real line, right? All the open sets, there's an infinite number of them, as there's infinite number of open intervals. Yeah. Okay, so there's idea of open sets. Okay, it's a very abstract concept. Examples of an open set is an open interval in a real line, as I pictured before. Okay, this is one way to do it. This is another way to do it. So I have some hollow points at the end to indicate it does not include its endpoint. Okay. A set is open if it does not contain any of its boundary point. So the picture I drew on the left here, this is an open interval. On the picture on the right is an open disk, right? It's a dotted line because that dotted line represents that it does not include all its boundary. That's why it's open. Okay. So I must admit that the definition of open and closed is going to be a little bit mind twister. So just, we're going to go over this definition carefully. Any collection of sets can be called open as long as the union of arbitrary number of open sets is still open, the intersection of a finite number of open sets is open, and the space itself is open. Okay, it's a little bit overloaded, but it basically talks about when can you call a collection of subsets to be open. For example, the collection of open intervals are open because the union of arbitrary of the open intervals, their union is always open, their intersection of the finite number is always open, and the space is also open. So sometimes the most widely used version is I have a subset from a Euclidean space in n dimension. A subset is open if given any point in the set there exists a real number, epsilon, such that for any points in the space, such that the disk of less than epsilon is in this set. Okay, so what does this mean? So for example, if I say this, if my n is equal to 1, right? A U is an open interval of R1. I'm saying that what I picture it is open is because if I choose any point in here, X in here, there exists an arbitrary neighborhood of radius epsilon such that every point with the distance less than epsilon is also in this open set. Okay. Of course, if my point is in the middle of this open interval, yes, I can always find a epsilon neighborhood where all its neighbor that is of distance less than epsilon is also part of the set. Of course, you can think about the extreme case. What's happened if my point is very close to the boundary? Not really at the boundary, but very close to the boundary. The beauty of this definition is that if my point is very close to the boundary, like where my arrow is pointing, there always exists a very small local neighborhood that has a positive radius such that all the points in the interior of this neighborhood is still part of the open set. Okay. So for example, if I have a point in the disk, I of course can find an open neighborhood where all its neighbors within distance at most epsilon, or does not include epsilon, is part of this disk. And if I have a point very close to the boundary, definitely not on the boundary, you know, there's always a non-zero neighborhood where all its points in this neighborhood is in my disk. Okay. So this is really the definition of an open set in Euclidean space. And then of course, a closed set is a set whose complement is an open set. Okay, so what is a complement? Complement is everything outside of it. So for example, if you talk about what is a complement of open set here, the complement of it is everything I drew in green that include the boundary point. Oh, sorry. This is the complement of open set. Now let's talk about complement of a closed set. If this is a closed set, which I'm using square bracket, well, this is a closed set and its complement is open. Okay. All right, that's about open set. So in point set topology, like I said, there's examples of topological space. Remember, X is a set, right? It's a set. So for example, if my X is a set of 3 points, 1, 2, and 3, and U is 0, 1, 2, 3, then what we call U, it's a topology on X. Okay, so this, if I picture it, there's an empty set and 1, 2, 3. This is the first example, how we visualize it in previous slides, right? So this is called trivial because the only subset of X that is in U is empty set in X itself. The other example is that if U is a power set, meaning that all possible subset, right? So actually this example here, what I highlighted in orange, this is a power set, right? It has an empty set, the set itself, and all its possible subset. Oh, no, actually, no, let me take it back. This is not. Let me take it back because if I want to make it into a power set, I need to have the one element set of 1 and 2, okay? So let me go back to the power set. The power set here is going to be the empty set, the set itself, the one element subset, 1, 2, 3, 2 element subset, 1, 2, 2, 3, and 1, 3. That is also a topology, okay? So if X is a real line, this is example I was talking about. If it's a real line, U is a set of all open intervals on the real line. That is a topology. And usually we just refer to X, the real line, to be a topological space because the set U, which is a set of all open interval, is kind of well understood, so kind of omitted in the description. But whenever you think about a topology, it is actually a pair, right? The set and a collection of subsets that satisfy those three conditions. All right, so the other concept that we need to go through is what is a continuous function? A continuous function is a function for which sufficiently small changes in the input result in arbitrary small changes in the output, right? That is sort of a high-level picture. There is a topological definition of a continuous function. Is it continuous if the pre-image of every open set is open? Okay, so now this function now is between a pair of topological space. But let's look at this situation where my topological space is just a real line. So this is sort of the example that we're most familiar with is a real valued function, okay? So if I give you an example here, this is a discontinuous function, is from R to R, and how do I define it? If I plot this function, is that it's equal, this function looks like it is equal to 0. Well, actually it goes to infinity on the left-hand side, is equal to 0 if X is smaller or equal to 0, and is equal to 1 if X is bigger than 0. Okay, so this is my function. Okay, this is a function from real line to real line. But what I'm saying is that this is not a continuous function because the pre-image of every open set is not open. So for example, in this case, if I choose an epsilon, and let's say epsilon is 1 over 2, for example, then I'm looking at, remember my range of this function is a real line. So I'm just taking an open interval in the real line, right? This is an open interval, so it's 1 minus 1/2 and plus 1/2. This is an open interval, right? But now what I'm looking at is the inverse of this open interval. Okay, so what is the inverse of the open interval if I were going to draw it? If I were going to draw it, it's actually the inverse of it is looking like this. Okay, and this is now not an open set. Okay, again, why is it? So for example, right, it contains a weird boundary points over this. Okay, so this is just an example of what is a continuous function in the concept of open sets. Again, you can also validate if I have a function which is simple. Let's say if my function f is from real line to real line, where specifically f of x is equal to x, right? So what is the image of this function? The image of this function is just a line that goes along the diagonal. So now if I take any open interval on the real line, sort of the pre-image of any open interval. So if I take the pre-image, okay, so I take this interval. Sorry, I think was a little bit confusing here. And I go to the inverse map, they are all open intervals. Okay, so actually I revert my explanation a little bit. Let me try to redo it. So because my function looks like this, I actually have to do the y-axis instead. So, but the idea is the same. Okay, so if I take, it says the pre-image of open set. Okay, so if I take a pre-image of, this is minus epsilon plus epsilon. So, okay, so ignore this explanation here because I just did it reversely. but everything else is the same. If I take minus epsilon epsilon, this is where I would like to see what functions give me here. It's actually give me the output of this is actually, so what I want to do, if f inverse of minus epsilon plus epsilon, well, epsilon, let's say is equal to 1/2, right, for the time being. What is this? This is saying that what function value give me, so what is the domain range that give me function value between minus epsilon plus epsilon? The only one given to me this is the one that give me 0, because that's what's falls in between. And that give me, if I'm going to picture in red, that give me everybody that is here.
Hi, Bei.
Yeah, go ahead.
By the definition, when x equals to 0, the y also equals to 0. So you make.
Oh, yeah, you are right. Actually, I drew it reversely. Yeah. Otherwise, this argument wouldn't hold. Sorry. This is solid, and this is open. Yeah. So because of this, the inverse map of this is actually goes one infinity to this, and this is not an open set because it. It's not an open set because it contains the point 0, and then 0 is a point on the boundary. Okay. All right. So let me finish today's lecture by describing the connectiveness of a topological space. We talk about connectiveness for a graph. Now we need to talk about path connectiveness for a topological space. A topological space is path connected is every pair of points is connected by a path. So again, thinking about my open disk, this is connected if any 2 point in the space is connected by some path. I can travel from one point to another. Okay. And this is a misspelling mistake, pre-image. And a path is a continuous function from the unit interval. Okay, so what does this mean? If I want to describe in a topological space a path between U to V, this can be described by a parameterized curve, essentially, which says that at gamma of 0, it's my starting point, and gamma of 1 is my, U and V. No. U, V. So my starting point is U, and my ending point is V. Okay. And oh yeah, so I'm going to end with a very strange topological space. So we're going to talk about a separation. We talk about separation of graphs. There's a separation of topological space. If you're talking about separation of a topological space, is that a separation of it is a partition into 2 non-empty open subsets that are disjoint. And a topological space is connected if it has no separation. Okay, so the first non-intuitive thing is connectiveness is weaker than path connectiveness. So the example I give here is what's called topologist sine curve. You know, topologist sits around and think about those really odd spaces. And this is one of those examples where the space is connected, but it's not path connected. Okay. So what is defined as is x coordinate is x and y coordinate is sine of 1/x. And x is in the range between 0 to 1 and include the points 0, 0. Okay. So this is going to be a really interesting reading for you. And one of the take home is I want you to convince yourself. You can even go to Wikipedia page describing the scientist sine curve, is that this is a space that is connected but not path connected. Okay, remember the definition of connectiveness is whether it can be separated into 2 non-empty open subsets as a disjoint. And path connectiveness has to be there's a path between any 2 points in the space. So it turns out in this space, there exists pair of points who cannot be reached from one another, but it's also a connected space. But of course, in practice, this kind of space only arises in very odd situations. Okay, So one of your take-home thing is to understand or convince yourself topologist sine curve is one of those interesting space that is connected but not path connected.